Hey, welcome back to Fat Mama Physics. In this video, we are going to talk about examples involving the Heisenberg's uncertainty principle. So at this point, hopefully you should have a general understanding of how the Heisenberg uncertainty principle works, where it is applied, and we're going to do some examples on that one. First, we're going to do example 1 here, in which we're going to look at looking at an electron that is confined inside a box of length L. And essentially what the purpose of this is trying to do is to show how an electron confined inside a box of size L is essentially how we model an electron confined in an atom. We can compare that with that of a nucleus versus as an atom, and then in question B, we're going to show how if an electron is confined inside a nucleus, the amount of energy that the uncertainty in its energy, or its kinetic energy, would be too great so that it could potentially just shatter the nucleus itself, which the energy itself will be much greater than the binding energy of, say, a nucleus. So let's begin. Example 1, an electron is confined in a box of size L. We want to show that the kinetic energy in this electron is at least Ek is equal to h in this expression over here, in which h is the Planck's constant, m is the mass of the electron, L is the size of the box. And for a hydrogen atom, we're going to use roughly that. With the uncertainty principle, we have delta x in position and delta p momenta is greater than h over 4 pi over here. We can use for this electron, we can say it could be anywhere inside this box, in which the uncertainty of the position we can say is L. In your textbook, in SOCOs, they use the uncertainty being half the size of L. In my opinion, it's going to be so inconsequential that it shouldn't matter. But if we use that, then we will get a factor of 8 down there. So I'm just going to use this for the sake of that. But when you do calculations on the IB exam, I've looked at some questions, and it does not seem it matters in which you take either the half the size of the L or the full size of the L to be on your uncertainty, since it's not going to matter so much anyways in terms of the magnitude, which is what we care about in this type of question. So there you go. If we use delta x as L is the half the length of the size of the box, then we are going to end up over here with L over 2 times delta P, which is greater or equal to this inequality H over 4 pi. If we rearrange this for delta P, then we are going to get delta P, the momentum, is going to be greater or equal to that's going to be 2H over 4 pi L. Okay, so when we do an estimation, we are going to, to find the kinetic energy, we're going to have to make an estimate. We're going to have to make an assumption. This assumption here is that the uncertainty in the momenta, we're going to say that this is roughly going to be the momenta itself, and we're just going to essentially look at the scale of which the scale of the energies inside for hydrogen atom. We're not going to get any sort of precise value. It's just an estimate. So we can make this assumption, and that's kind of saying that we're looking at the range of momentum anywhere from 0 to a maximum of p is what kind of we're saying. But all of this is in an estimation. So if we make this assumption moving forward, then we are able to show, we will able to use this as the momentum to estimate the kinetic energy of this electron, in which we know that the kinetic energy is momentum squared over 2m. So if we put this expression inside here, we're going to get Ek is equal to 2h over 4 pi L all of this squared divided by 2m. And we're going to simplify this. This is going to be h squared, and then 2 over 4. This is going to cancel and make this a 2 here. Over 2 squared is going to be 4 pi squared L squared all over 2m. And just putting all of this on the bottom, that's going to be h squared over 4 on the bottom with the 2. 4 times 2 is 8. We have pi squared L squared and m. Okay, so that shows this here is similar to that. But I wouldn't even care about this L over 2. And if we didn't include this one, let me write it in a different color. So if we say delta x is just approximately the length of the box, then we would get this delta p over here as greater or equal to, so this 2 wouldn't exist, so that just be L over 4 pi L. And if we substitute that inside our kinetic energy expression, which all of this gets squared, then we're going to have the 4 squared, which is going to be 14, and then sent to the bottom, that's going to make it 32. So, I mean, yeah, it's, there's some difference for sure. Everything else is going to be the same. So that's pretty, so that would be the difference, okay? Anyhow, we should probably solve this over here, which was basically what we wanted to do, was to estimate the electron's kinetic energy in electron volts. So we're running a little bit out of space. I just made that over there smaller so we can have a little bit more space. I'm going to do the remaining here in red to estimate the size of an atom. So for an atom, we use 10 to the power of negative 10 meters for the size of this box. Okay, and then putting all of this in, we're going to get, I get 6.111 times 10 to the power of negative 19. And this question wants an electron volts, so I'm going to divide this by 1.6 times 10 to the power negative 19. This is joules per electron volts. And this is going to give us roughly, for the scale of energy, about, I get 3.8, which is roughly about 4 electron volts. This is on the order of 1 or 2 or how many electron volts, which is within range of what we see for the actual kinetic energy of these electrons. And this is quite a bit much smaller than the speed of light, so we don't have to worry about relativistic effects here. So we can just directly assume that the kinetic energy is momentum squared over 2m. Now we're going to use the same model, and we are going to show that what happens if we try to confine an electron inside a nucleus and why that is not possible. So let's see what happens if we confine this electron inside a nucleus, in which I'm going to use the uncertainty in our position to be exactly the length of the box. So we'll see how that plays out. So I'm not going to use, I'm going to start from scratch from the Heisenberg's uncertainty principle, in which the uncertainty in the momentum is going to be h over 4 pi, and then L is going to come down on the bottom over L. So then solving for this, we're going to get, and for the length of the nucleus, or the particle in the box, I'm going to use the, instead 10 to the power of negative 15, which is shown more examples. This one here I grabbed from Cognity, but I see more of the 10 to the power of negative 15 instead. So I am going to use that for my particle in the box. And this is going to give us 5.2 ... times 10 to the power of negative 20 kilogram times meters per seconds. Okay, so then that's going to be our momentum. And then taking our momentum and finding the kinetic energy associated, like the previous question, we're going to assume that this uncertainty in this momentum is going to be approximately the momentum itself, as just an estimation. Of course, it's not doesn't have any, that's not the purpose. We're just trying to do an estimation so that this kinetic energy, that we can use that to find how much, find the kinetic energy of this electron. So this is what we get for the kinetic energy, and once we solve this, that is going to be 1.52 dot 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 times 10 to the power negative 9. And if we divide this by trying to find the electron volts, this is going to be roughly 9,548-ish mega electron volts. So that's approximately about 10,000 mega electron volts. And if you compare this to the binding energies of certain nuclei, that's 10 to the power 4, then you're going to get, that's going to be a lot larger than the binding energy of a lot of nuclei, so that's going to essentially rip up the nucleus itself. So that's another reason why an electron cannot be confined inside a nucleus. It could potentially do that, okay? So there we go. This is Heisenberg uncertainty principle, and at this point we essentially are just grazing over this. There's so much subtlety here that we're not even able to touch on, which is outside the scope of this course. Otherwise, the math and everything else will be too complicated. So we kind of have to just appreciate it from we do some rough calculations to get some rough qualitative idea, and that's the best that we can do at this level. So we've developed some appreciation through these examples. We have one more looking at the Heisenberg uncertainty principle in terms of time and the lifespan of a particle in terms of its uncertainty in the energy. So stay tuned for the next example. Thank you for watching. Fat Mama Physics signing out.